Let's start with a famous statement made by the well-known Marquis de Sade. And he stated, he formulated, let's make a last effort, citoyen, in order to accomplish our French Revolution. What he had in mind was the transition from the political revolution to the sexual one. But now the last effort of mine will be dedicated to the foreseeable future. I shall begin with some historical words on the origins of networks and the internet and its principle and its structural role for the future of computing. But just a few words because Hendrik Speck, as my successor in this course, will make this his main topic. The theory of networks has begun in the 30s of the last century when AT&T had the telephone and telegraph monopoly in the USA, and problems of jam and others led to a theory of many parallel networks, cables, many cross points between cables, and the application finally of mathematical tools like topology and graph theory to really existing infrastructure, communication infrastructure. This kind of questioning and anti-jam measures were continued by Shannon in the aftermath of WW2, and for reasons I'll skip. Shannon himself, he was a great, he was a real handicraft man, built up an iron labyrinth with an iron mouse called Theseus, obviously, from Ariadne, and Theseus and the Cretan labyrinth of King Minos. And under this chessboard-like visible surface, the electronic was hidden on the invisible surface back. And the labyrinth was quadratic. The fields of the labyrinth were quadratic. The resulting labyrinth also quadratic. And Shannon, with his hands, there's a little documentary film, that's why I know it, could lay down walls and could put up walls and put the mouse at any thinkable place inside those walls and the labyrinth. And if not all walls stood up, the mouse by its own artificial intelligence was able to find the way out of the labyrinth. But when Shannon surrounded his little mouse with walls on all four sides, his face became rather melancholic, and he says now the mouse is trapped as we would trapped in the same situation. And then at the end of the little 10-minute film, he spoke on many anti-rockets that find their way to the enemy in parallel. and AT&T, the Musik.
Like the music that is a logo?
Yeah, the musical logo of AT&T ended this little film. This was the theoretical and equally practical origin, what the DARPA scientific department of the Pentagon took on in the 70s, I think, with the basic idea of mail packets finding their way by themselves. Packets, little parts of messages that traveled around in a labyrinthic topology, in a labyrinthic grid of many possible paths, and in case they were not trapped, they came on many different unpredictable ways from the start to the goal. And this new concept of communication way coincided with the strategic decision of not of the DARPA but of the Pentagon head to change the Cold War defense and attack system from one central hidden command deep under Mount Cheyenne in Dakota to very little, very small, distributed, about 30, in fact 26 I think, small bungalow commands, each of which should be able to replace destroyed command posts by a Soviet attack. So surprising attack, and so the 26 all visible and not hidden but small command posts distributed all over the United States were connected by a grid and not just by a cable. And as you know better than me, some elite universities were included in this network grid. At first, 2 or 3 universities, in the next step, all universities, .edu, and finally, virtually everybody of us. And now it's my beg to you that you don't confuse personal communication with intercomputer communication. In fact, it's your computer or your computers, in plural, that are connected, that are interconnected by many possible mouse-like paths. And it's not you that are addressed or addressing, it's your net address. Just for each of your computers, there is another address. You may be unique, but your computers are not. Therefore, in my eyes, the human factor in Twitter, in Facebook and so on is not so important as it may seem. It's rather sometimes a hype, just as the reader's letter to the good old London Times in the 1870s. A little bit more interesting seems to me the interconnection of big servers and individual interests, commercial and intellectual and theoretical, by big search machines and companies such as Google. The Google search and priority algorithm, I've been told by the Google Germany. He was a software engineer and surprised to find someone interested not in the commercial aspects but in the programming aspects of Prince machine. The real problems Google itself experiences right now are the competitors. They try to reverse engineer the search algorithm of Google to find out the actual today weights of priority 1.099 up to 0.01, and to guess these priority system preferences in the Google algorithm and to out-hero, so to say, so that the companies that are part of Google's presentation that come to the first list places on the today list, and this is a war between Google and the commercial companies on a worldwide scale, and so the rates have to be changed every day almost. Also, the fundamental search algorithm is still the good old Stanford University algorithm written by Donald Knuth, one of the founding fathers of software programming. But on a half commercial, half political level, this dominance of Google explains a bit the actual decline, commercial decline and Wall Street decline of Microsoft. Operating systems offered on the market are obviously not so important as they were in the near past. The operating system is transferred more or less to the servers, and the programs running under the operating system are transferred to the servers, and the servers are just like packet switching. They find their way to the end consumer by their own labyrinthic mouses, and so all the community of, let's say, Google servers build what Google calls, you may know, the cloud. And the cloud provides anything the user need, and Redmond, that is Microsoft, has seen its better days. I don't know whether I'm be able to fill out this last effort with enough information for you, so it could be that we have large time. Because in the following, in what I said, probably I made some error in supposing that you are somehow familiar with the theory of graphs, be they directed or not. Maybe it will suffice to draw a little diagram for you. Now I have to decide how many points, how many strategic command quarters I will suppose. Let's say 6 or 7. A little bit too symmetric.
It's a very nice flower.
It's a flower.
I reproduce it, I double it. That's much too perfect. I'm too inclined to aesthetic. First I draw a little scheme for undirected graphs. Das heißt Kanten, edges. These are the points of the graph, and the points are the points of the graph, and the lines are the so-called edges. And it's absolutely non-important whether these edges and these points correspond to telephone connections or to strategic connections, to some geometrical object or to the internet. It's the connecting itself that defines the graph. And this melancholic point is not connected at all. It is the last letter lost in solitude. And now with another connection scheme, I try to represent a directed graph. And which can be traveled only in the arrow's direction and not in the other direction. And so after my choice for directions, you see that there's another isolated point, and second you see that this graph can't be run like a circle, because the directions contradict each other. So that's a rather useless form of connection. Maybe these two simple diagrams make things a little bit more clear as models for your memory. Now we come to the hardest part, the playing the oracle. Moore's law, notwithstanding its mathematical elegance and purity, is bound to fail one day. Exponential growth exists only in mathematics and not in any physical or environmental reality. This is a point that Thomas Pynchon's novels make again and again, that only an economy of exchange is a stable one and an exponential, whereas an exponential one, that is a capitalistic economy, has a built-in break point, failure point. It's asymmetrical from the start on, and the dreams one day have to disappear. We have seen it, or we are seeing it in the almost exponential curve of oil production, and the peak is about to be overwritten, and the curves are falling, as in the diagram of the page before. At the beginning, oil production in the early 20th century started almost as an exponential function, reached a saddle point or a saddle state, and now, since these very years, it's declining, and I've been told by the German aerospace company that the last drop of oil will fall into desert sand about 2070, if we don't take care. But on the other hand, it's really fantastic, this Moore's law and the Moore's law and its concrete implementations, as I explained you, I think, as roadmaps for the next 10, 12 years. Every year or every half year, Intel and IBM and AMD and so on publish their plan for the future. I'm not sure whether I've touched this topic enough. And these roadmaps all try to realize in the foreseeable near future the continuous existence and value of Moore's law. And this is a crazy concept of law. One of my younger doctorants, Dr. Aspirant, is about to working on the specific structure of this law, the roadmaps are neither physical nor human, that is engineers' laws. There are some in between nature and technology. There are prescriptions, self-definitions, plans, concepts with strict boundary conditions, with investments in astronomic dollar heights, because new fabrics have to be planned, smaller structures of silicon chips, tools to produce and to write into these smaller structures in nanometer dimensions. And it's the most innovative kind of industrial planning I'm conscious of. But defining this roadmap is a fight against many physical enemies. And can again be, strangely enough, illustrated by water systems, hydraulic systems. The transistors on the chip become smaller and smaller. The channels on chip become narrower and narrower. That is, the speed of electricity or the speed of water in narrower channels slows down. The electricity inside digital chips, the electricity flow or velocity inside silicon chips lies decades under that in the vacuum, the absolute velocity of light. It's rather like schleichen. It's rather like sneaking, in a sense, as in a very small little creek. And not only the velocity comes down, but the walls of the channels, the isolators against loss of water, alias negative electrons, don't remain dense and secure, but the very small dams are leaking, and electricity flows out from the channel into parts of the chip where no electricity should flow. So, in other words, the environment, the internal environment, becomes even more muddy, if I may stay with hydraulic comparisons. And these we call the physical limits set to silicon technology as such. In the very near foreseeable future, we will, continuing this roadmap, this path, arrive at levels of miniaturization where the behavior of the CPU becomes unpredictable and disturbed by randomness.
So they're scribing at the molecular level now, right? They're just doing beams.
Yeah.
How much smaller can you get than that?
About 5 nanometer to my knowledge.
Even than a beam? Wow.
Now we are at 30 nanometer and 10 or hopefully 5 would be the absolute limit. I'm not on the molecular level anymore, but on the electron level and the atomic level of silicon and silicon dioxide. And there are no way around to this deadlock in the near future. Nature will not look into her own eyes anymore, but into muddy waters which don't reflect anything. So, a switch in materialities, materials, and design has either already been taken or will be taken in the immediate future. And one of the most promising candidates is light, as you know. Photons as the particles carrying light, equivalent to electrons in electronics, and in fact arising from the event when one electron jumps from a certain almost cyclical level of planetary motion to another planetary motion around the nuclear kernel, and thereby emitting a photon. Photons are candidates, have been not just candidates, but photons are already in use, as everybody of you know, and could be possible candidates for whole computing universal machine systems. Here the order of my notes becomes a little bit confused. Everyone, I think, has a certain concept of glass fibers instead of electrical cables or wires. And these days they are heavily used and put into the earth because they are vulnerable. They have to be shielded, so to say. And they are shields by themselves. I just told you the terrible future of silicon connections on chip. Their capacity to isolate electricity from non-electricity becomes weaker and weaker. The dam breaks. Some Pink Floyd song from Dark Side comes into my mind, but only dimly. The dam will break or something like this in brain damage. Whereas glass fibers are perfect isolators. Inside there is light instead of electricity, and outside there's maybe what else you have. But between the shielding walls of the glass fiber, the light ray I introduced with ray tracing this morning is perfectly protected from interception, from noise, from distortion, from leaking. Because seen from the inside, now you put yourself into this very small, narrow tube, narrow and lengthy. Fibers can be produced, I think, some kilometers with a length of some kilometers, and a circle of some millimeters or so, and these are only approximations of my incomplete knowledge. But inside, however, this cyclic inside is measured in structure. It's secure that it's an almost perfect mirror. Not a plane mirror, but a cyclic mirror. So the photon stream, alias the ray, entering the fiber is reflected on and on, depending on its entry angle by trigonometric laws. And so it is propagated from the start to the end of the fiber of the cable, and in terms of the theory of graphs, this is an undirected graph. The functions of start and end point can be interchanged. And it's even possible, technically, the most important point is that the light also transmitted by this mirroring, ongoing mirroring inside the fiber. This light is monophasic, that is, each ray has one and only one precise frequency. It's precisely this kind of science defining one ray, and this cyan, this green-blue, may without any problem coexist with a darker red ray, and with a blue ray, and a yellow ray, and all defined by frequencies or wavelengths of light. The sun sends, as you know, a polyphasic light and a multicolored light, an all-spectral light, as Isaac Newton with his prism proved experimentally, and a sun's light, let's call us white. White is the sum of all spectral frequencies, but our eyes are not able to distinguish these frequencies as such from another. We just see the mixture, the addition, or like pots, where every color is mixed up to white or to black in the case of subtractive addition. But our eyes and our monitors are additive synthesizers or analyzers of light. We see red, green, blue parts of light. Printers, digital printers have another concept of elementary three colors: magenta and yellow and purple, I think. And they need black in order to print out as a fourth elementary color or non-color to produce texts and convincing printouts of pictures. But how do we get these monophasic, many spectral lights? The simple answer: by taking a laser as the input of the glass fiber. Laser light is monophasic light by definition and has the property, all the properties I mentioned.
Is there a difference in the power carriage of an electron versus a photon?
The power?
Yeah, so telecommunications use fiber optics now,
Yeah.
right? But they're not being used to transmit power, they're being used to transmit signal.
Ja, ich möchte wissen, ob es einen Unterschied gibt in der Energietransportfähigkeit
Power,
zwischen
ja.
Elektronen und Photonen. Was Sie bisher erklärt haben, ist ja Signaltransport.
But there's, to my knowledge, there's almost no resistance, there's almost no loss. So, and the power is not decreased from start to end point, whereas electrons inside the chips or inside the buses, and this is what concerns the computer technology. As I explained, the power goes down and down, following the roadmaps. By truly following the roadmaps, things become versatile for electrons and their power to transmit information. And I've even read a book by an English named Chambers, Basics of Communication and Coding, I think was the title. It's long ago, I read it on the Pacific River or Strand, on the Pacific beach of Santa Barbara, long time ago. And Chambers said that under ideal conditions, one photon could represent one unit of information, that is 1 bit. And under ideal conditions, Chambers understood the cosmic vacuum. But he continued to say that we were not as far to this ideal minimal signaling photon, but a book written in the 90s or late 80s told me, its reader, that under experimental or under the bedingungen of expensive lab technology, some only about 200 photons could be detected as 1 bit, and the difference between 1 and 200 in his or mine eyes isn't too big. And in the meantime, between 85 and 2010, things surely have deeply have been made more. The number of 200 has been reduced to an unknown number to me, to a number unknown to me. This was an answer? So la la.
Sorry.
I think, as I understand this, the question is not so much energy or power, but speed. Photons inside the glass fiber run almost at absolute speed. This is the power of the actual internet inside cities and on long distances. The remaining problems lie on the last 10 meters or last 100 meters from the final photonic endpoint to our computer or dial, also to our modem, what was in older days called modem. The telephone or cable companies are horrified by these last 20 or 100 meters and the horrible financial expansions to connect every household with a glass fiber net cable from the final distribution point to up to our living room. At least in Germany, this is a problem for cities and big cities, not to speak from small villages. They are absolutely not connected by glass fiber systems, but still by copper cables. And the actual government, Angela Angie, has put much money in improving the situation, especially on the rural side. Otherwise, we'll lose some characteristics of democracy on the bedingungen of internet communication. Hopefully, you see this poor little or happy little photon bouncing from reflecting wall to wall without any resistance and loss of energy almost. And word almost I just used brings me to the last restriction of this almost ideal communication system. In sad reality, there is some loss, even in glass fibers. So from time to time the ich erkläre Ihnen das, kann ja später. Relay systems have this disadvantage since the time of their invention. And in order to fill your and my time with nice stories, I go back to the first historian we had, the great Herodotus of Halikarnassos in Minor Asia. He was not the first Greek historian to work, but his forerunners are almost lost, very few years and others. But Herodotus' Historiae are preserved verbatim in all 9 books. They tell us the story of the struggle, of the wars between the Persians and the Greeks since time immemorial, starting with the Trojanic War, the Trojans as the forerunners of the Persians, and the Achaeans as the forerunner of the Greeks of the time of Herodot. So from Helen and Paris to passing through Marathon and Salamis to the latest Greek colony founded in Greece, that is in southern Italy, where Herodot himself died after having read his 9 books to the Athenians, which were deeply flattered by Herodot's praise of Marathon and Salamis. But in other books of his Historiae, Herodotus gives quite different stories, not so Hellenocentric, but really curious about foreign cultures and peoples, Egyptian, Persian, Scythian, African, and so on and so on and so on. Only Rome and Italy are lags in these 9 books. And so we learn, I think in the 5th book, that the Persian kings, had an optimal communication system inside their empire, their huge empire, incomparably better than any Greek little state or town could call its own. From Persepolis, the metropolis, the command, the general staff, the command point, an imperial road run for almost 1,000 miles down to the blue coast of the Mediterranean and to Greek cities under Persian rule, Milet, Ephesus, Halikarnassos, and so on. And this imperial or royal road was managed by horses, riders, functioning as messengers and relay posts. The first rider started with the first horse from Persepolis, because the empire, the first empire to our knowledge and to Hegel's knowledge, was hierarchical and top-down. The first horse and rider started from Persepolis, but after 30 miles or 40 kilometers, the horse was exhausted, the rider was okay, because he was carried by the horse. And so the rider continued to be the same, and his measures continued to be the same. It was a imperial, one of the many imperial commands to his so-called satraps. And the exhaust and the relay station, a little house or bigger house, housed a certain amount of fresh horses, and so the rider chose the freshest horse and continued for the next 30 miles. And so he jumped, so to say, under 10 or a dozen horses down to from Persepolis to Sardes on the coast of the Mediterranean, and delivered his message in a speed which was only surpassed by the Roman imperial cursus publicus, installed by the first emperor Augustus. As Harold Adam Innes has shown in 1950 by his courses before the British Imperial Council, I think, at the very moment where the Empire of Britain dissolved into nothing, the Canadian Innes gave the definition of what is an empire. It's a far-reaching, fast communication system which ideally is not just one line as a Persian communication system, but a whole graph, a whole grid of connected graphs or edges. I can't give you without looking up my Herodot edition, the precise numbering of this beautiful description inside the 5th book of Herodot's Historiae, but you will find it surely by the register. And I end with saying that somehow I feel myself reminded of Herodotus when I do what I do for you, because at the very beginning in the first book somewhere, I think he states that his job is legen talegomena, to say what has been said. Legen talegomena. And so Herodotus confesses that he couldn't test or control every information he got from others or try to get himself. It's from hearsay, it's a mix of hearsay and oral history and written history and hidden history and secret service history I've given to you, and I will have given couldn't guarantee it all. And this is, since Herodotus, the problem of us historians. Now to switch back from ancient history, which is, as you see, not just Eurocentric, but interested on the enemy or adversary, and the other, as you would say with your deconstructing of feminist American language, the big other, I mean. To come back to photons and glass fiber communication systems, something is specific to them that I couldn't possibly modelize by horses and their riders. Horses are tired, can be tired, and riders can be tired. This is the positive comparison point between the Persian Angaraion, the imperial road system, and photons. But one marvelous property of photons is missing in this human communication system, or animal-human communication system. Riders are not immune against interception. A hidden enemy can stop them, can kill them, can take their message from their dead body and bring it, to, let's say, to the Greeks. A traitor inside the empire. And the most important property of photons inside their small glass fibers is their immunity against interception. And this is a point that will pass through my last lecture from now on. How much immunity in Claude Shannon's sense can a channel arrive at? Take, once again, electrical cables, which are electromagnetical coils in final, and capacitors in final analysis. There's no copper cable without a certain amount of farad or microfarad and a certain amount of Henry, of inductivity. And by this very fact, copper wires are not immune to interception. They send electromagnetic fields, they build up electromagnetic fields in their neighborhood, in fields in the sense of Clark Maxwell, and an enemy can intercept these fields without even solder his interception line to the cable. This would be very silly because the CIA would see immediately that the Soviet Secret Service had made an attack on the cable, but intercept its inductivity or its capacity without touch, simply by neighborhood, would go more undetected. The enemy would be not sure of detection himself, but more immune. Yeah. In the Cold War, heroic exploits on both sides are known, and the hottest spot of the Cold War, as all of New York know, was the divided city of Berlin. And in the Berlin underground, so many subways and so many water channels for fresh water and for
sewage. You mean the sewage system?
no. And the opposite of drinking water would be
I think it's called sewage. Because sewage serves for both. It can transport.
Could you
fresh
say it
water,
louder? I don't
dirty
understand
water,
anything.
dirty water, right? It's Kanalisation. Es geht um die sewage.
Ich verstehe es halt nicht.
Kanalisation.
Das verstehe ich, aber das Wort für Schmutzwasser verstehe ich überhaupt nicht.
Das Wort gilt für beides.
Nein, das habe ich doch verstanden. Ich möchte aber umgekehrt ein Wort für Scheißwasser.
Letztes Wasser,
Das habe ich verstanden.
Water mains and sewage pipes.
Ja, Sewage. Yeah, thank you. It was just a phonetical problem between Tanya and me, but I wanted to connect positively to what Tanya has told you yesterday about Rudolf Virchow and this the great physician at the end of the 19th century who had made Berlin an exemplary canalization system for his time. Berlin became a model for the separation between sewerage canalization channels and drink water channels, whereas in other cities all of this still got mixed. And so I wanted to say that Berlin since 1900 about was like some Emmental cheese. Made up of holes and whole communication systems, and so the CIA and American secret services and the Russian secret services could easily come to open-lying telegraph cables or telephone cables, and until they were detected, it usually took some years. Or they built themselves new tunnels deep under the wall of Berlin and got from west to east or from east to west. Okay? And this was an awful state of affairs for both sides, east and west and east. And so Glasfaser channels came into play at just the right moment in the history of secret services and their ongoing duels. They are much more immune to interception, honest totally immune. And that's why the first big application of glass fiber systems was not for us poor end users or for big companies or something like this, but for the NATO, to my knowledge. The Atlantic was full of telegraph underwater cables, as we had seen before yesterday, and now all of them were replaced for secrecy reasons, or many of them were replaced by secret glass fiber transatlantic connections. To my knowledge, the first such transatlantic line started in the German harbor of Bremerhaven and went to some point and the coastline of on the east coast of the US, I would suppose, but I'm absolutely no information about the end point of the cable or the start point of the cable, but I would guess it might have been Langley and the place where the NSA has its headquarters in Virginia. And so, once again, and probably for the last time in my long history, high-level technology in its origin is connected to a military and exclusively military use, and then it spreads and spreads on to big companies and communication companies and universities and finally to all of us. Okay, but I'm almost at my end, not just. Yes, I forgot something very important. We always have a certain tendency to forget bad news, or not to deliver bad news. Bad news in the case of photonic connections, channels and fiber lines is that because of the certain amount of power or energy loss, the photon stream after some kilometers or decades of kilometers have to be refreshed by a relay station. This was the comparison point. And to my knowledge, its optical amplifiers are still a monstrously big desideratum. In Edinburgh and other universities, optical amplifiers of optical signals